Good day, everyone. I am Francema Nansala, and along with my design partner, Runil J. Gabiola, and today we'll present our electrical design for a proposed two-story multi-purpose building. So here you can see the table of contents. Electrical plans starting with the general notes and specifications up to short circuit analysis. Next is the legends and symbols used in the design, and of course, the location which is in the Iba city of Tayabas, Quezon. So, looking closely at our riser diagram, the power passes from the MVSG to our 750 kVA transformer, then branches through ATS-A and B. This ensures uninterrupted operation by seamlessly shifting critical loads to our backup 750 kVA generator set during emergency utility outages. Power is cleanly isolated in the LVSG main distribution panels for the ground floor and second floor, and dedicated sub-panels like the LPAHU, LP elevator, and fire pump panel.
For the architectural layout, starting with the separated fire pump room from the main building, and then moving on to the main building, we have the electrical room for the ground floor, we have the mechanical room, and then we have the admin's office with a small space office. And then we have the law firm that has small spaces offices, and then the meeting rooms. And then we have the convenience store that has its own office, dry storage, and the chiller. And then we have the janitor's room, and then we have the public toilet room. And then located at the center of the building, we have the elevator. And then we have the restaurant 1 and 2 that has their own kitchen, chiller, dry storage, and office. And then we have the coffee stall 1 and 2 that have their own dry storage and offices. And then moving on to the second floor, we have another electrical room. And then we have an admin's office for the second floor that has a big office. And then we have the general office space that have small offices, a conference room, a toilet rooms, and then we have the pantry. And then again located at the center is the elevator, and then we have the public toilets. And then moving on, we have the retail store 1 and 2 that have their own storage room and the offices and the fitting rooms. And then for the gym, we have our workout spaces. We have the office, we have the male and the female changing room with their own dedicated sauna rooms. Moving to the lighting layout, the design placement of the luminaires across the center and the corner zones are specific ambient and task lighting requirements for using the 16 wattage LED fixture ceiling mounted is utilized throughout the most areas. However, high lumen 26 wattage LED tubular lights were deployed in the convenience store shopping aisles and the gym workout areas. Control switches are positioned immediately after the room entrances and near the administrative control points, except the sauna switch, which is mandated to be located outside the wet environment. The layout also details the connection lines to clearly delineate the intended switch groupings and the branch circuit networks. Finally, for the power layout, the service entrance begins with the 750 kVA pad-mounted transformer and then the standby generator set. Internally, the ground floor electrical room is detailed to map out the legally required working clearances around the medium and the low voltage switch gears, and then the automatic transfer switch units. To maintain the safety, the branch circuit panel boards are securely isolated in the dry storage areas or positioned in the low traffic hallway corners in the office suites. The power layout explicitly utilizes the standard abbreviation for the special and dedicated outlets, and then the HVAC loads, including the cassette and the split type air conditioning units, are physically centralized on the plans to optimize the thermal management for each specific spaces. Lastly, strict code compliance is demonstrated through the deployment of the ground fault circuit interrupter and the weatherproof receptacles in all wet or open areas, such as the public toilets or the primary hallways.
For the design analysis, this part of electrical plan focuses on calculating the demand load and total current of the building. In our analysis, we first identify the different types of electrical loads present in the building. This includes general lighting, general receptacle loads, small appliances, air conditioning units, and other loads and motors. Each of these loads was calculated in volt amperes based on their rated power and quantity. After determining the individual loads, we applied the demand factors based on the Philippine Electrical Code to obtain the total demand of the building. After the calculations, we have computed a total demand of 533,380 VA. From the total demand load, we have computed the total demand current of 769.89 amperes using the standard three-phase electrical formula. This allowed us to determine the proper ratings of main conductor, circuit breakers, transformer, generator, and capacitor bank that we'll be using in the system. So for the schedule of loads, we have here the panels, MVSG, LVSG, FPP, LPE, LPAHU, LPLF, MDPGF, MDPSF, and panel boards 1 to 12. Every panel board in this design was analyzed using exact demand calculations, overcurrent protection sizing, and maintain imbalances safely under the standard 10% variance margin. Now, moving on to the voltage drop, we have here the formulas. Z total is equal to the square root of R squared plus JX squared. For a single phase, the voltage drop is equal to 2 times the current multiplied by the total impedance. And for a three-phase, the voltage drop is equal to 1.732 times the current multiplied by the total impedance. So looking at the transformer below, it is the connection from ATSA to LVSG, and below it is the cable size. That is obtained from the load schedule, particularly in the line of main conduit. Next is the length. It is measured from the layout in CAD application from where is the ATSA up to the location of the LVSG. For its resistance and reactance, this is per 305 meters, and its value is obtained from the PEC, particularly the AC resistance and reactance for 600 volt cables. So for the current, it's obtainable again in the load sched. And by calculating the voltage drop, we use the formulas above. For the percentage drop, the values here are all less than 5%. And the process of getting the values are same here from LVSG, from MDPs to PB, farthest convenience outlet loads, farthest lighting loads, and farthest three-phase loads.
To start our short circuit analysis, we first reference the single line diagram. This models the physical connection path from the utility drop through the transformer down to the individual branch panel boards. It details the ampere trip and the ampere frame sizes at each node, along with the physical line impedances. These line impedances were derived by multiplying the cable's known resistance and reactance by the physical run length over the standard 305 meter constant. In this model, the fire pump funnel, LPAHU, LPLEV, and LPAC are designated as lumped active motor loads to account for their fault contribution. In total, we identified 22 critical fault points, which are individually modeled in the subsequent pages with independent impedance diagrams to clearly illustrate how the Thevenin equivalent impedance is resolved for each node. Moving on to the computation phase, we establish our per unit base parameters. We utilize a 1000 MVA short circuit baseline, a system base apparent power of 0.75 MVA across the regional base voltages of 34.5 kV and 400 volts. The utility impedance was calculated by dividing the MVA base by the MVA-SC, yielding a 0.075% reactance. Next, adhering strictly to the IEEE standard for 141, we applied a subtransient reactance of 17% for all active induction motors. For the 750 kVA transformer, we utilized the manufacturer's actual impedance of 5.75% alongside of a X over R ratio of 4.5 sourced from the IEEE standards. This resulted in a resolved transformer resistance of 1.24735% and a reactance of 5.61308%. To standardize these values, physical ohmic impedance were converted to the per unit system using the formula Z is equal to S base multiplied by the Z actual all over the 10 multiplied by KV squared base, where the denominator equates to 1.6 at the secondary region. Motor contributions were similarly converted by multiplying the 17% subtransient reactance by the ratio of the S base over the motor's operating apparent power. Following the per unit conversions, the impedance diagrams were simplified to extract the Thevenin equivalent impedance at every specific fault point. Using this value, the symmetrical short circuit current was computed utilizing the formula. For the symmetrical, we have the 100 all over the absolute value of the ZTH percentage multiplied by the S base all over square root of 3 multiplied by the B base. To account for the worst case first cycle DC offset, the asymmetrical short circuit current was calculated at the 125% of the symmetrical value. As shown in our summary table, this maximum asymmetrical fault current ultimately dictated the minimum required CAIC rating for every circuit breaker, to which we applied a minimum of 30% safety margin to ensure absolute structural safety. Finally, we move to the bill of quantities. This section details the comprehensive procurement specifications required to this commercial design. It itemized the equipment, copper conductors, raceways, and auxiliary materials alongside the projected labor costs. Pricing the data was cross-referenced with current market rates from the authorized electrical distributors operating within the Philippines, ensuring that all specified equipment is either locally stocked or readily available for regional shipping. Accounting for all materials, equipment procurement, and labor installations, the proposed electrical infrastructure design for this two-story multipurpose building totals an estimated capital expenditure of 43,980,717.39 pesos. This concludes our presentation. Thank you for your time, and we are now open for any questions.